Earlier, we briefly mentioned the chi-square test statistic, and now we want to look more at chi-squared tests. There are many different kinds of chi-squared tests we can perform. We'll look at 3 of them, and then in particular, we'll focus on one. So one kind of chi-squared test that we can do is a chi-squared test for homogeneity, where we take a sample from 2 groups and essentially compare their probability distributions. So an example of a question we could answer here is whether or not gender has an effect on pet preference. So if we were to ask men and women whether they prefer cats, dogs, or some other kind of pet, and then create a table of our data, it might look something like this. We can see that what we're doing here is sampling from 2 groups. One group is men, one group is women, and we are comparing their probability distributions. So we have a probability distribution for men across cats, dogs, and other pets, and then the same probability distribution for women. Now, if gender has no effect at all on pet preference, then we would expect those probability distributions to be similar. In other words, if men prefer cats at roughly a 25% rate, dogs at 50%, and other pets at 25%, then we would expect roughly the same distribution for women, 25% for cats, 50% for dogs, and 25% for other pets. Now, of course, we know that these 2 distributions are very unlikely to be identical, but if gender doesn't affect pet preference, then we could expect them to be roughly similar. But if gender does have an effect on pet preference, then we might see these probability distributions being extremely different, and the chi-squared test statistic lets us look at how different the distributions are and then determine whether the difference is big enough to be called statistically significant, such that we could reject the null hypothesis that gender doesn't affect pet preference and therefore lend support to the alternative hypothesis that pet preference is affected by gender. So that's one kind of test we can run. Another kind of test we can run with chi-squared is a chi-squared test for association or independence. In this kind of test, we sample from one group and we compare characteristics for that same group. For instance, we could compare eye color and handedness, so whether someone is left-handed or right-handed, for the same set of individuals. We might make a data table that looks like this. So we pull a sample of people, all from the same population, and we record whether they are left-handed or right-handed in contrast with their eye color. So out of our one group, we can see that we have 72 people who are left-handed with brown eyes, 36 people who are left-handed with blue eyes, 130 people who are right-handed with green eyes, etc. So in this kind of test, our null hypothesis would be that eye color and handedness are independent. They're not associated. They have no association. And therefore, the alternative hypothesis would state that eye color and handedness are associated. They are dependent. And we would, again, similar to the homogeneity test, look at the distributions of the left-handed people and the right-handed people. If handedness and eye color are not associated, then the distributions for left-handed and right-handed should be similar. But if handedness and eye color are associated, if they're dependent on one another, then maybe we'll see different distributions for left-handed and right-handed people. And if that difference is significant enough, then we may be able to reject the null and lend support to our alternative hypothesis that handedness and eye color are associated variables. So you can see how these 2 kinds of tests are similar. The third kind of test we'll look at is a chi-squared goodness of fit test. And here we're comparing actual versus expected values in a contingency table. For example, we might try to answer the question, are sales, number of sales of a product, affected by month? And maybe we would use this table here where we have the months of the year, January, February, March, etc. And we have the number of sales that we make in each month. So we call this a contingency table because the number of sales are contingent on the month of the year. To answer this kind of a question, we would think about the expected number of sales in each month based on the total number of sales for the year. In other words, if sales aren't really impacted by month, then we would expect a steady level or a consistent level of sales across the year. Month wouldn't have an effect on sales, and sales should remain fairly steady. And so, in that sense, just like with these 2 tests, we would compare the distribution of actual sales to the distribution of expected sales. And if those 2 distributions are significantly different enough, then we might be able to conclude that sales are affected by month. So that gives you a little bit of an idea of what we're doing with chi-squared tests. Let's dig into this goodness of fit test in a little more detail so that we can see an example and work through a full chi-squared test. So we're starting here with an expanded version of the table that we had for the goodness of fit test. We're trying to figure out if sales are affected by month. So we had the months of the year. These were the observed number of sales in each month. So in January, we sold 60 products. In February, we sold 80 products, etc. And when we total up all those sales, we have 1,020 sales for the year. Now, if we take 1,020 and we divide it by 12 months in the year, we get 85. And so our expected value for each month of the year is 85, because if month has no effect on number of sales, then sales should remain steady, and our expected value would be a steady, consistent 85 sales per month for a total at the end of the year of 1,020 sales. What we want to do now is use a chi-squared goodness of fit test. We're going to pick a confidence level of 95% or an alpha value of 0.05, an alpha value of 5%. And we're going to use this chi-squared test to make a determination about whether sales are affected by month of the year. So with all of these chi-squared tests, our null hypothesis is that month has no effect or that the distributions aren't different. Basically, that the two variables don't affect each other. In this case, that observed and expected values aren't different. So we would say here that sales aren't affected by month. That means that our null hypothesis then is that sales are affected by month, or that the month of the year does have an effect on sales. So again, if sales aren't affected by month, then it would make sense that they would be evenly distributed over each month, and we would see something fairly consistent like this expected value of 85. Now, keep in mind here that we can't just lend support to the alternative hypothesis that sales are affected by month just by having different observed values than the value that we expect. For instance, if our observed values were 84 for January, 86 for February, 84 for March, 86 for April, 84 for May, 86 for June, etc., yes, those values are technically different than the expected values of 85 for every single month, but the values are so similar, they're consistent enough that the difference will not be statistically significant, and we will not have enough evidence to reject the null hypothesis and therefore lend support to the alternative. These observed values here not only have to be different, they have to be different enough to meet our level of statistical significance. And that's what we'll determine with our chi-squared test statistic. So to calculate chi-squared, that's our next step. For each of our data points, we find the difference between the observed and expected values. So we take observed value minus expected value. That should kind of remind us of the idea of the residual that we've been looking at as we've been working through regression here. So we take the observed minus expected, and we get that difference. And so we can see here that the third row in our table is observed minus expected. Then we square that value to make all the values positive. That's the last row of our table, all those squared values. Once we have all those squared values, we add them all up and then divide by the expected value. We divide each one of them by the expected value, and then we add all of those results together. In this particular chi-squared test, because the expected values are all the same, that means we can add all these squared values in the fourth row and then just divide by 85 all at once. So the sum here of this fourth row is 6850, which means that the chi-squared test statistic for this particular test will be 6850 divided by our expected value, 85, which is approximately 80.59. So this is our chi-squared test statistic. Just like we would calculate a t-test statistic or a z-score, we calculate this chi-squared test statistic. And then, as you might have suspected, just like the t-score or the z-score, we need to look this up in a chi-squared table. Chi-squared has its own distribution, and so it has its own table. And the chi-squared table looks like this. It's very similar to the t-table in the sense that we have a degrees of freedom value down this left-hand side. Now, when we think about degrees of freedom for a chi-squared test, we always need to go back to the table that we're starting with. And we want to look at the original data that we had, the observed data, including the total. So in this case, we would be looking at this part right here of our table, all the original observed data plus the total. Now, the degrees of freedom is the number of values that we would have to include in the body of the table, not including the total, in order to be able to fill in any other missing values in the table. So here's what we mean. If we look at the body of this table, we have all these values in the body, 60, 80, 65, all the way up to 65 here in December. And then we have the total. The question is, how many values can we remove from the body of the table before we would no longer know what to put in each cell? Well, if we remove the value here in December, and we pretend now that we don't have the value for December, the only values we have are January through November and the total, the question is, could we figure out what value to put back in for December? And of course, the answer is yes, because we could take the total, 1,020, and subtract from it all of these other values for January through November. And what we would be left with is 65, which has to be December's value. So we can remove the value for December, and we can still know what all of the values in the table will be. Now the question becomes, can we remove another value from the body of the table and still know how to fill in the rest of the table? So let's say we remove November's value. Now the question is, can we accurately fill in November and December? And the answer is no, because we have the total 1,020, but if we subtract out all these values, January through October, we're left with a missing 125. But we don't know how to split 125 between November and December. We have no way of telling how much of that 125 goes in November and how much goes in December, which means that we can only remove one value from the table before we would no longer be able to finish filling it in. So if we can only remove one value, that means we have 11 values remaining in the table, which means in this case that degrees of freedom is 11. Degrees of freedom is the remaining number of values that we have in the table. And since that's a little confusing, let's look at one of the tables we had from earlier in the video, this handedness versus eye color table. Really what this comes down to is that when we look at the body of the table, we're always able to remove the last row and or column of the table. So in this table, we could remove all of these values because you can see that even if we didn't have any of these values here, we could find left-handed Hazel by subtracting 72, 36, and 20 from this 140 total on the right-hand side. That would allow us to fill in this left-handed Hazel here. So then we would have this value. And then once we have that value, we can fill in right-handed and brown by subtracting 72 from 532. So we'd have that value. We would find right-handed and blue by subtracting 36 from 251, and so on. We'd take 150 minus 20 to get this cell, and then 67 minus 12 to find this cell, and suddenly we'd have the whole table again. So if we're able to remove all of these values here, that means degrees of freedom for this table, for this scenario, is 3, because the number of remaining values in the body of our table is 3. We have 72, 36, and 20. And so degrees of freedom here would be 3 in the same way that degrees of freedom up here would be 11. So back to our original example, our sales affected by month, we have 11 degrees of freedom, and we're interested in this 5% significant level. So we come here to 11 degrees of freedom, and we work our way across to an upper tail probability of 0.05, whatever our level of significance is. We find that in the upper tail probability header row, and then we come here to their intersection, and we see this value, 19.68. From here, the only thing left to say is whether our chi-squared test statistic that we calculated is less than or greater than the value that we find in our chi-squared table. In this case, we can see obviously that 80.59 is greater than 19.68. And whenever we find a chi-squared test statistic that is greater than this critical value that we find in the chi-squared table, that means that the test statistic we found is significant enough to allow us to reject the null hypothesis. In our case, there's a massive difference between 80.59 and 19.68, which tells us that we have very, very strong evidence that sales are indeed affected by month of the year. So we can reject this null hypothesis that sales aren't affected by month, and we give a lot of support because of the massive difference here. We give a lot of support to this alternative hypothesis, the hypothesis that sales are indeed affected by month of the year, that the distribution of sales doesn't just hold steady and constant, unaffected as we go month to month, and that instead they fluctuate with some level of significance, and the number of sales we make is dictated by the month of the year. It's affected by month of the year. So in a way, we could say that month of the year and sales are dependent variables. They are associated. They are not independent of one another. So even though we looked at different kinds of chi-squared tests, they all follow this same kind of general pattern. We're always comparing two different distributions, and we sort of start with this idea that the distributions are the same, and so we compute this expected value. Then we look at the difference between actual value or observed value and expected value, and we use this formula to calculate the chi-squared test statistic. Once we have the chi-squared test statistic and the number of degrees of freedom, we can look for our level of significance in the chi-squared table and compare our test statistic to the value that we find in the table and use the relationship between the test statistic and the value from the table to make a conclusion about whether or not we can reject the null hypothesis.